Hi, sorry I couldn't be with you on Thursday. I'd like to take this opportunity, though, since I got you on the video over here, to tell you about reaction quotient. There aren't any problems in this chapter on the ALEX for reaction quotient, but reaction quotient is an important concept in equilibrium, and I noticed that the ALEX homework covers reaction quotient a little later when we do thermodynamics. But I'm gonna find a couple problems from one of your textbooks, the TRO textbook, which is online, and I'm gonna adapt them to make them a little bit harder. Yes, that's right, a little bit harder. Let me tell you what this means, this reaction quotient. So you know that if you have some kind of chemical reaction, like this, let's say they're all gases, all right? So if they're all gases, then every one of these species is going to be involved in the equilibrium expression. Am I right? And assuming that this is going to go to equilibrium, as things are wont to do in this universe, this would be the equilibrium expression. Do you agree? It is possible that I may make some error in here, and if I do, please use the question and answer forum to share your suspicion with your fellow students. Let me show you where that is. The question and answer forum is right here. You can swap ideas and let me know if I have made some mistake. Alright, so that is the equilibrium expression. Now, at equilibrium, the pressure of gas C and the pressure of gas A and the pressure of gas B will all multiply and divide to get you the Kp. Let's pretend the Kp is 0.0051, all right? So 0.0051 will equal the pressure of the C squared divided by the pressure of the A divided by the pressure of the B, right? Of course, I mean, you've been doing homework just like that. So, what if we're not at equilibrium? What if you just added a whole bunch more of C, right? What if you just got a whole bunch more of this and you just threw it into the container and it's not at equilibrium? You know that, according to Le Chatelier's principle, this reaction will shift to make more what? More C or more A and B? That's right. It will shift to make more A and B. But that's just conceptual, you know, it's qualitative, you know. Oh, you added more C, so Le Chatelier's principle says that it's going to shift, the equilibrium is going to shift to the left. We're going to make more A and B. But how can you program that? Like, how can you use numbers to show that it will happen the way you say? How can you prove your hypothesis using numbers? Or, better yet, how can you program a gas sensor device so that it will trigger some signal to you when this is going to happen? How can you make this a systematic decision instead of a conceptual, hand-wavy kind of decision, instead of a qualitative decision? How can you pin this decision down using numbers? Am I getting the point across here? All right, so here's how you do it. You take the reaction quotient Q. Q equals the products over the reactants when you are not at equilibrium. Like this. Look, it's the same thing. It's exactly the same thing as the equilibrium expression, except we are not at equilibrium. So, suppose the new concentration of C, so we're talking about the initial concentration of C, I mean, the initial pressure of C plus the added pressure of C, right? So that constitutes the new C, right? Divided by the PA, let's say the PA was maybe 0.02 atmospheres, right? And divided by the PB, let's say the PB was also 0.02 atmospheres, all right? So what is what new pressure of C do you require in order to get equilibrium? So, right, so first of all, what if the old what if the old pressure of C plus the added pressure of C equals a whopping 5 atmospheres, all right? So 5 atmospheres, meaning we added a lot of C. So in that case, so we're going to square this. So the new pressure of C is 5 atmospheres, so we square that. So that's 25 divided by 0.004, all right? 25 divided by 0.004 is a really huge number. You know, you don't even have to calculate it. 25 divided by 0.004, you don't even have to calculate it. You just know it's a huge number. And that's the key right here. If you know that your current Q is greater than your equilibrium constant, then that means your reaction will shift to the left. If you know that your current Q is less than your equilibrium constant, guess which way your reaction will shift? That's right. It will shift to the right. Okay? Do you get that? I have made some problems for you. All right. So let me help you out with these couple of problems here. So I made the problems in the module called equilibrium. I took these problems from your textbook, but they made them a little bit harder, you know, because textbook problems are so boring. All right. So here we go. Look at this reaction. All right. So this. And let me get you a new page here. All right, so this is a new page. This is a reaction. Now I have these numbers here. For you, you're going to have the same Kc, but your numbers here, these numbers are going to change for you. Okay, so for you, your numbers are going to change, but for me right now, these are my numbers. So let me first write the. So the question is, what is the current Q? All right, so let me write the expression for Q based on this equation. Q equals, let's see, the products, NH3 and H2S, NH3 and H2S, divided by the reactants. Oh, look, the reactants are all solid. So that means I need to write them here, right? Wrong! I got you, didn't I? Hope you got an eraser. Okay, anyways, so the Q equals here, I'm going to plug stuff in, 0.427 and 0.667. 0.427 and 0.667. And those are molar, but nobody cares about the units because there are no units for Q or for K. Okay? All right. So what does that equal? So I get the K calc. Whoops. Where's the K calc? Where is it? Have you eaten it? Okay, here it is. So it is 0.427 times 0.667. It's 0.285. So the Q is, where's the pen? The Q is equal to 0.285. Now, is 0.285, so that is the answer, by the way. So for me, the answer is 0.285, okay? Write down that answer because I'm going to ask you this in the homework, just to make sure you watched this video. I know who you are. All right. So, now, that's the dog. There's no problem here. All right, so now, my question for you here in this video is this reaction going to go to the left or to the right? Is the equilibrium going to shift right now to the left or to the right? All right, so let's see. See, there's the equilibrium, right? And my Q right now is compared to the K. My Q is actually a lot greater than the K. All right? So since the Q is a lot greater than the K, I'm products heavy. And if I'm products heavy, which way is it going to shift? To the left or to the right? I'm not going to tell you. You're going to tell me on the homework. Okay. So I have another question here. And this question is harder. This question is actually a lot harder. All right, so let me go through this with you. My numbers are, as you see here, your numbers are going to be completely different. Okay? So let's see. Well, the Kc is going to be the same. So I've got this equation. So let me copy down the equation as a first step, just to warm up the brain. Let the brain know that we're about to do an equilibrium problem. Is your brain warmed up? I know, with this weather, it's hard not to be warmed up, right? All right, so the Kc is equal to 0.0085 again. Have you noticed that this is kind of extraneous information for these problems? So what is, oh, actually, for this problem it's not extraneous. So the question is, what is the minimum amount of hydrogen sulfide, or dihydrogen sulfide? Dihydrogen monosulfide? Gas, which you must add if you want to bring this reaction to equilibrium without having any excess ammonia gas. Wow, that was a mouthful. What do I mean by that? Here's what I mean. I mean that this is a 92-liter container. So in my 92-liter container, this is 92 liters, I have 0.955 molar NH3. And there is no H2S. What I'm saying is, how much H2S? I'm talking about how many grams, by the way. Yeah, that's why it's hard, because I'm talking about grams, right? So how much H2S do you need to put in here to bring this system to equilibrium, this equation to equilibrium, without wasting any ammonia gas? Meaning I want to use all the ammonia gas. Okay, the reason why I say without any excess ammonia gas is because you could put any number of grams of hydrogen sulfide in here, H2S. You could put 1 gram of hydrogen sulfide in here, and this system will come to equilibrium. You're going to have a lot of excess. Let me rephrase that. You could put 1 microgram of H2S gas in here, and this will come to equilibrium. You're going to have a lot of excess ammonia gas, because 1 microgram of hydrogen sulfide gas is like 300 times less than 1 micromole of hydrogen sulfide gas. And this container is almost 100 liters. So this is almost no hydrogen sulfide gas at all. So it's going to come to equilibrium, but with a whole bunch of extra ammonia gas. That's not what I want. I'm asking for you to use all of the ammonia gas, right? But, see, I know what you're thinking. Okay, well, if I need to use all the ammonia gas, let me just put 1 gigagram of H2S. Yeah, smarty pants, that's not going to work, because my question is, what is the minimum amount of H2S gas which you must add? So I'm telling you, you got to take into consideration the actual amount of ammonia gas you have here, right? And you need to stoichiometrically determine how much H2S you need to use all of that to bring this to equilibrium. You know what I'm saying? I want this to be at equilibrium, and it needs to be using the minimum amount of this gas and using all of the available this gas, but at equilibrium. Okay? I'm going to work this problem out for you right now using my numbers. On the homework, you're going to have different numbers. So here we go. Let me erase these ridiculous 1 microgram and 1 gigagram, because that's not what we're doing here. So, you know that Q equals, is this balanced, by the way? Oh, it is balanced. Okay, well, the next problem is not going to be balanced. All right, so, well, maybe. So Q equals the reactants, the products. Yeah, these are the products over the reactants. And the reactants are solid, so I ignore those. So the Q is going to equal 0.955 molar times the H2S. Now I'm going to call the H2S the X, all right? So I want to know, what is the concentration of H2S? In other words, what is the X that I need to make Q equal to Kc, all right? So I want Q to be equal to Kc, because that is when this system, this chemical equation, will be at equilibrium, when Q equals Kc. That is the key concept with reaction quotient, okay? Do you see how this problems-based approach is working here? All right, so here we go. How do I solve for x? Well, I'm gonna plug in the Kc here, right? And I'm gonna put 0.955 here, right? I think you know where this is going. I'm gonna divide both sides by 0.955, by 0.955. Sorry about the handwriting. Ha! You thought your lab instructor's handwriting was bad. You know, I'm doing my best here, though. You know, because I'm using a digital tablet, and it's not pencil and paper, so that's why it's bad. So here we go. Here we go with 0.0085 divided by 0.955, and I got 0.0089. Well, and this is a two significant figure problem because KC only has two significant figures, so I got 0.0089. So my x is equal to 0.0089. Oh, great! So that's great. 0.0089 molar. I'm done, right? Wrong! The question is asking for grams of H2S. So, see, what is the minimum amount of H2S gas? Now, if you give the answer in molar, nobody can measure out for you a certain molarity of hydrogen sulfide gas. That's impossible. There's no machine that dispenses molar of hydrogen sulfide gas. There's no machine like that. You need to find your answer in moles and then convert to grams, because there is a machine that dispenses gases in grams. In fact, your car probably has a machine like that. There's a mass flow sensor next to the air filter in your car, and it measures the air intake coming into your car's engine because your car uses oxygen. The mass airflow sensor does a little calculation as to how many grams of air. Well, anyways, yes. Oh, soon. Okay, so anyways, back to the problem. So I'm going to change this to moles and then change it to grams. So how do you change this to moles? Well, looky here. We've got a little volume here. And you know, molar means moles over liters. So I'm going to multiply this by the liters. So the liters cancel out. You see that? So that gives me the moles. But I'm not done yet. All right? I'm going to multiply the moles. Where's the pen? Oh, here it is. I'm going to multiply the moles. So liters canceled out, so now I have moles. I'm going to multiply the result of this calculation, 0.0089 times 92.0 liters, times the molar mass of H2S. Now, I believe the molar mass of H2S is about 34.1 grams for 1 mole. So the moles on the bottom cancel with the moles on top, and so the grams are what we have left. So the answer is 0.0089 times 92 times 34.1. The answer is 28 grams. So you need to add 28 grams of H2S. 28 grams of, and that is the answer. Did you catch all those steps? If not, the solution is simple. You just play it back. Just rewind the YouTube video a little bit. You can make the YouTube video play at twice the normal speed if you want, or you can make it play at half the normal speed if you want. Just Google how to adjust YouTube speed setting, and then you will see how to do that. So anyways, I'm going to put 28 here, 28 grams. Please do not write the units in the Canvas answer box for these problems because I didn't design this like that. I designed it so that the computer will calculate what he thinks the answer is, and he will compare it to what you think the answer is. Canvas does not know anything about significant figures, so when she shows you the answer, it might have a lot of significant figures. Don't worry about it. I asked her to accept all answers within a certain error, and your answer, if you have the correct significant figures, will be within a certain error. For example, for this problem, I haven't yet, but I'm going to ask Canvas to accept all answers within plus or minus 1 gram. So if you answer 27 point blah, 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 that will be fine. If you answer 29, that will be fine. 28 point blah, 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 that would also be fine. Okay, so next problem. Guess what? This problem is even harder. Yeah, that's right. Do you know why it's harder? It's because you are smart. You took Chem 101 and you passed it. You are capable of this. And so let's exercise that brain, shall we? Let's go. So we've got a long equation here. Oh my God, why did he give us this long equation? Actually, it's not a long equation. Whoops. What happened? Oh, my preview's gone. Oh, rats. Okay, here we go. Here's my preview. All right, so it's not a long equation. Sorry, it's not a long equation. I thought this was going to be a long equation, but it's not. All right, so Here we go. So first of all, let me copy down that chemical equation. I thought this wasn't balanced, but you know what? It actually is balanced. But there is a coefficient here making things harder. You know, I love to make things harder for you. The reason is, I know that you're smart. I know you can do it. And you know, what good is being smart if you're not going to use it, right? So Kc is 1.1 times 10 to the minus 5 at 298K. You might wonder why the problems in the homework are always, oh, the K at a certain temperature, or they give you a certain temperature. This temperature is not important for this problem. But the thing is, the K, equilibrium constant K, changes at different temperatures, which you saw happen in the lab, didn't you? All right. So we've got a 5.5 liter solution. All right. So it's a solution. So I'll just put it in a big old beaker. This huge 5.5 liter solution in a really big beaker, bigger than whatever you've ever seen, I guess. Now it has 5.7 grams of dissolved silver sulfate. Now silver sulfate is this. Now suppose you want some solid silver sulfate. Oh, okay, so this is dissolved, but you want it to be solid, which makes sense. I mean, if you want to collect the silver sulfate. So when you add sodium sulfate, oh, what's this? Sodium sulfate? What is this coming from? Don't worry. Nobody cares about the sodium here. Why? Because there is no sodium in the chemical equation. Sodium sulfate is only a source of sulfate. If you put more sulfate, that is a disturbance to the equilibrium. If you put more sulfate, Le Chatelier says, of course, this equilibrium will shift to the right, right? Wrong! It will shift to the left, silly. That's right. It will shift to the left. Okay. So, the equilibrium shifts to the left when you add more sulfate, or when you add more silver. But I ask you, what's cheaper to add, sulfate or silver? Am I right? Right. So that's why we add sodium sulfate, just because we want to add sulfate. So we add sodium sulfate, and the question is, at what minimum amount of sodium sulfate added will the precipitation process start? Now you might think that this problem is like the previous problem, but I gotta tell you, it is not. It is much harder. And let me show you what's going on with this, all right? So the Q is equal to Ag plus squared times SO4 2 minus. And we already know the molarity of Ag plus, all right? Because we have these grams. Here, let me change these grams into moles. So, I believe that the molar mass is something like 311.799 grams in 1 mole of Ag2SO4. Okay? You can please verify that on the periodic table. You do need to use the correct molar mass, regardless of whether mine is correct or not. If you want to get the homework problem right, that is, and you may notice that I have inflated the points. Oh, actually, I made this only 1 point because this is the extra hard problem. Like, if you cannot get this problem, don't worry, you could still get an A, but you're just not going to get, like, the highest A. I don't know. It's all right. So, what was I doing? Oh, yes. So I need the molarity of the silver plus ion. So notice that in 1 mole of Ag2SO4, there are 2 moles of Ag plus. You see? That was difficult. You should play that back if you didn't catch that, all right? Now, once I get the moles here, right? So once I get the moles, I will divide that by, I will divide everything by, I will divide this entire thing, I'll divide this entire thing by the volume, because molarity, which is what the square brackets indicate, molarity means moles per liter. So there it is, 5.5 liters. So let me show you how this looks on my calculator. It looks different on your calculator, of course, but you know, it's fun to see what Glenn's doing on his calculator sometimes. Times 2, and I'm gonna say that it's 0.037 moles. But you know, I'm not gonna trim this at all, because this is all multiplication division. I'll trim it at the end. Don't worry. So divided by 5.5 liters. So that's 0.0066 molar. So what I've got in here is Q Q equals 0.0066 molar. But it's squared. Yeah, it's squared, baby. So don't forget about the squared. And now this SO42 minus, let's say that this is X, right? Actually, I've been using X as a time sign, so let's just say that this is M for molarity. Well, M, yeah, I'll say this is M for molarity. Actually, I'm going to say it's big M. I'm going to say it's big M for molarity, okay? So this is the unknown. I want to know the molarity of the sulfate ion. So when how do I figure out the molarity of the sulfate ion that is required to make precipitation happen? Well, what is Q when precipitation starts to happen? Q is none other than Kc. At equilibrium, that's when precipitation starts to happen. Remember, at equilibrium, the reaction goes back and forth, but there is no net change, right? So at equilibrium, you are at the tipping point. So these precipitation will start to occur at equilibrium. That's when it will start. You got to understand that is the definition of that is part and parcel of the definition of equilibrium. If it's a precipitation reaction at equilibrium, yeah, the precipitation starts. Also, at equilibrium, the precipitation ends. It starts and ends at the same spot, equilibrium. It's kind of like the melting point of water. Like if you have 0 degree water, right? That's ice, yeah? It is freezing and it is melting and is going back and forth at equilibrium if you are at 0 degrees. Back and forth, back and forth. Okay, so anyways, at Kc, the precipitation will begin. And I can just continue to add sodium sulfate to get more and more and more and more and more and more silver sulfate precipitate. All right? So let me solve for this M by dividing 0.0066 squared on both sides. Okay? Now, please notice my calculator technique here. I'm going to use a fancy Kung Fu style move over here. Not that I know Kung Fu. So I'm going to square this. So there it is. I'm using the square button. Boom. You see, I didn't have to trim any sig figs off of this. And then I'm going to say 1 over x, effectively putting this at the bottom of a fraction. There it is. And now I have just accomplished this part right here, 0.0066 squared on the bottom, right? And Kc is on the top. What is Kc? This is Kc. 1.1 times 10 to the negative fifth. So this now is a times problem. Times 1.1 times 10 to the negative fifth. Negative fifth. There you go. So I've got a two significant figure, 0.25 molar as the answer. So the M equals 0.25 molar. Okay, so for those of you for whom it has been a little while since your last math class, instant replay of what just happened here. I had the answer to 0.0066 squared, and then I put 1 over that, and then I multiplied that by 1.1 times 10 to the negative fifth, because that's the Kc, effectively getting me the Kc over 0.0066 squared. You see, it is the same thing as what is scrawled on this scratch paper here. Not that it's paper. So anyways, I solve for the molarity. Remember, this is the molarity of the sulfate ion. All right, so this is the molarity of the sulfate ion. Is this the right answer? Of course not. That would be too easy. The question doesn't ask for the molarity of the sulfate ion. The question asks the amount of added sodium sulfate. That amount is going to have to be in grams, because I ask you, when you do a lab experiment, do you add sodium sulfate to some reaction mixture in moles? Can you go to the electronic balance and measure out moles of sodium sulfate? No, of course not. You have to do it in grams. And so this answer needs to be in grams. All right? So let's get a little bigger here. Let's get a lot bigger here. All right. All right, so here we go. So I have a target molarity for the sulfate ion. It is 0.25 molar. I need to know how many grams of sodium sulfate I need to add to achieve this target molarity, 0.25 molar. But remember, there was already 5.7 grams of silver sulfate in here. meaning there is already some sulfate ion in here. How much sulfate ion? Well, let's change everything to moles so we can figure that out. So, how do you change this to moles? Molarity means moles per liter. All right? So, if we multiply by liters, given here is 5.5 liters, I guarantee you, your number of liters is not going to be the same as mine. All right, so the liters cancel, and we have the moles. 0.25 times 5.5. That's 1.4, or 1.375. So I've got 1.4 moles. So I have 1.4 moles of, I need 1.4 moles of sulfate ion. But how many moles of sulfate ion? So this is needed, right? This is needed. So I need that many moles of sulfate ion. But how many moles of sulfate ion do I already have? Well, let's see. 5.7 grams of silver sulfate. Is this hard? Oh, yeah, you bet this is hard, yeah. Is your brain working? I hope so, yeah. So, I happen to have this sneaking suspicion that that is the molar mass of silver sulfate. Right? Now, for 1 mole of silver sulfate, you get 1 mole of sulfate ions. Are you aware of that? I'm sure you are. And the grams will cancel, and the moles will cancel. So that's moles of silver sulfate. So now, I do 1.4 minus, where's the pen? Where's the pen? Who ate the pen? Where's the pen? What? Okay, here it is. Okay. So 1.4 minus whatever number of moles this multiplication and division gets me, okay? Now notice, when I do this on the calculator, I do not clear the display and type 1.4. No, I'm just going to leave this here, this excessively precise number here, and then I'm going to type a minus sign, and 5.7 divide 311.799 times 1, which nobody has to actually do, and I will get 1.4. Oh, so the amount of silver sulfate that I have is negligible. Ah, well. That was not my intention when I created this problem. I didn't mean for it to be negligible. But for my particular iteration of this problem, it is negligible. I do not know if it will be negligible for yours because I gave Canvas a wide range of numbers to use. So it may not be negligible for your problem. You had better watch out for that. All right? So I need to add 1.4 moles of sulfate ion. Must add. I must add. I must add. All right? I must add 1.4 moles of sulfate ion. But how can I obtain 1.4 moles of sulfate ion? Watch carefully. 1.4 moles of sulfate ion. Okay, if you already know, stop the video and do the homework. But if you don't know, then please watch. Watch carefully. So, you can find 1 mole of sulfate ion in 1 mole of sodium sulfate. Am I right? Of course I'm right. Not that I'm always right, of course. I think you have seen me be wrong in lecture many times. So, but how are you going to measure out moles of sodium sulfate? Impossible. So, because we are civilized human beings, we convert the sodium sulfate to 2 grams. I believe this is the molar mass of sodium sulfate. I could be wrong. You must verify this using the periodic table. You must use the correct molar mass for sodium sulfate. Otherwise, you will get the wrong answer. I am wicked. And you know what? I like it. I actually like it. All right, so 198. So we're only using 2 significant figures here. And so this rounds to 200. So this is 200. This is 200 grams of sodium sulfate. It is possible that Canvas will not do the significant figures correctly because, as I said before, Canvas doesn't know how to do significant figures. So if it marks you wrong, just do it again, please, and just put a few more significant figures. Canvas does not know the rules. I try to ask Canvas to accept a certain amount of error, in order to make up for its lack of knowledge of significant figures, but sometimes that fails for certain iterations of this problem. And so that is my final answer. And here I go back here and I type the number 200. All right, and that is how to do the homework. I'm about to add a couple of problems here. The answer to those problems you will find at the beginning of this video. Thank you. Bye. How do you turn off the video again? Oh, yes.